What is a trajectory, and how do we analyze the speed of an object as it travels in the air?
In this video, we will teach you about projectile motion and its velocity using a simple experiment like throwing a golf ball in the air.
Projectile motion is defined as the motion with constant horizontal velocity and constant vertical acceleration due to gravity. So you can see we can break down this motion into its horizontal and vertical components. As this ball travels in the air, its horizontal velocity remains constant.
Although the slope is not entirely constant across all of the points are represented by a linear regression. This means that they have an average slope that fits the equation y equals mx plus b. In the linear equation, m represents the slope of the line, which is the same for any given value for x. Therefore, the slope is constant. Since the slope of a distance versus time graph is equal to velocity, then the velocity is also constant. Therefore, in this situation, the horizontal velocity of the green ball is constant.
When looking at the plotted points for vertical distance versus time, they can be represented by a quadratic regression. However, a quadratic equation does not have a constant slope, as the line is curved, not straight. However, you can determine the instantaneous velocity at any given value for x by calculating the derivative of the equation. Therefore, in this situation, the vertical velocity of the green ball increases as the slope of the parabola also increases as time continues. While the horizontal velocity remains unchanged, vertical velocity changes at a constant acceleration due to gravity. Looking at the data exclusively gathered from vertical displacement, we can see that the vertical motion exhibits a parabolic trajectory. The slope of the graph is not linear. This means that the vertical velocity increases because of acceleration downward.
The estimated equation for horizontal motion is displacement as a function of time equals 1.5t plus 0.01, where dx stands for horizontal displacement in meters and t stands for time in seconds, and time must be larger or equal to 0. The estimated equation for vertical motion is displacement as a function of time equals negative 7.38 x squared plus 0.83, where dy stands for vertical displacement in meters and t stands for time in seconds, and time must be larger or equal to 0. The instantaneous horizontal velocity and vertical velocity for a given time can be calculated using the horizontal displacement versus time and the vertical displacement versus time graphs. For this question, t equals 0.2 was arbitrarily chosen. The instantaneous velocity was then calculated through the derivative of each function as follows. In the previously mentioned graphs, we obtained the equation for the horizontal displacement of the ball, which was equal to 1.5t plus 0.01. From this equation, we can derive the velocity. Our function would then become vx t equals 1.5. Therefore, the instantaneous horizontal velocity when t equals 0.2 seconds is 1.5 meters per second. Again, from the previously seen graphs, we can obtain the equation for the vertical displacement, which is equal to negative 7.38 t squared plus 0.83. From this equation, we can derive the equation for the velocity, which is equal to negative 14.76 t. To obtain the instantaneous vertical velocity at the point chosen, we have to replace the value chosen into the t in the equation, getting negative 14.76 times 0.2, thus getting a value of negative 2.92. Therefore, the instantaneous vertical velocity when t equals 0.2 seconds is approximately negative 2.92 meters per second.
For a given time, we can calculate the vertical and horizontal instantaneous velocities separately.
No way!
And combine them to get the overall velocity at that point.
Oh wow!
Let's look at the velocity when time equals 0.25 seconds. To find the instantaneous velocity, we take the derivative of the function and simply substitute 0.25.
So cool!
To calculate the instantaneous velocity for the projectile at t equals 0.2, we use the horizontal velocity and the vertical velocity previously obtained. When we draw the vector diagram, we can observe that we need the Pythagorean theorem in order to obtain the instantaneous velocity. We would get the following equation. Instantaneous velocity is equal to the square root of the horizontal velocity, which is equal to 1.5 squared, plus vertical velocity, which is equal to negative 2.92 squared. We would get a value of 3.28. Therefore, the instantaneous velocity of the projectile at time equals 0.2 seconds is equal to 3.28 meters per second. Now that we have a good understanding of projectile motion, we will use an inline simulator to examine height and range of projectiles. For part A, launch angle and vertical displacement are the variables which we will be testing. Initial velocity is fixed. We chose initial velocity as 15 meters per second and acceleration due to gravity equals 9.8 meters per second squared, where g is positive in the definition of the formula. The angles 30, 45, 60, 90, and 95 degrees were tested. Both the calculations and the simulation supported the fact that 90 degrees yields maximum height given the same initial velocity and acceleration due to gravity. The results were as follows. For part B, we calculate the time in the air. Given the initial velocity equals 50 meters per second, the angle is 30 degrees, the acceleration due to gravity is negative 9.80 meters per second squared, and the vertical displacement is 0. We use one of the motion equations. To get the result, the time equals 0 or 5.1 seconds. We will observe this result in the following picture. We will try angles 35, 40, 45, 50, and 55 degrees to arrive at the best angle for max range, given the initial velocity equals 50 meters per second and the acceleration due to gravity is 9.8 meters per second squared. The results are as follows. For part D, we need to calculate range using the equation dx equals velocity squared times sine of 2 times angle over acceleration due to gravity, given that the initial velocity equals 50 meters per second and the acceleration due to gravity is 9.8 meters per second squared, and the angle is equal to 30 degrees. After calculation, we find that the horizontal displacement is equal to 220.92. And we got from the simulation that the horizontal displacement should be 223 meters. For part E, we need to show how to calculate the angle or velocity a projectile must be fired at to hit a target. First, we show how to determine the angle. Using the equation dx equals velocity squared times sine of 2 times angle over the acceleration due to gravity, given that the horizontal displacement equals 17.24 meters, the velocity is equal to 50 meters per second, and the acceleration due to gravity is equal to 9.8 meters per second squared. We get a calculated angle of 1.94 degrees and a simulation angle of 1.94 degrees. Now we determine the velocity at which it must be fired at to hit the target. Using the equation dx equals velocity squared times sine 2 times angle over acceleration due to gravity, and given the variables chosen, which are horizontal displacement equals 15.46 meters, the angle is 5 degrees, and the acceleration due to gravity is 9.8 meters per second, we get a calculated velocity of 29.54 and a simulation velocity of 29.54.